Okay, Assalamualaikum warahmatullahi wabarakatuh and hello. So we continue our study with magnetic core losses, which is slide number 53 if not mistaken. Okay, yes, 54. Okay, so this is basically go back to the theory. Okay, so first when this topic is started, it start with the theory and then we continue with calculation of the circuit and then we continue back with the theory. Okay, sorry, but the notes are kind of not organized properly, but make sure you try to understand it. Okay, so let me change the pen first. Okay, so recall back your B hash curve. Okay, remember B hash curve. Okay, B is equals to mu hash. So because this is constant, okay, this is linear equation basically. So this is B, this is hash. So basically the relationship is something like this. This is, the gradient is mu. Okay, so that is the theory of the B hash curve. Okay, and remember F is equals to Ni equals to hash L. Okay, so basically the higher the current or the higher the number of turn, the higher the hash. Okay, so basically when you increase the current, you increase the hash. Okay, the higher the hash, the higher the current, the higher the hash. Okay, L is constant because you cannot change the length. Okay, and when you increase the hash, also you increase the B. Okay, so basically something like that, but this is in ideal condition. So in reality, it's not looking something like this. Okay, so let me move this. So in reality, this one, okay, this is B, this is hash. So at the beginning, it looks something like straight line, like a linear equation, which is B equals to mu hash. But after certain time, after you increase the current too much, it will go something like this. Okay, so this one is called saturated. Okay, so basically when you increase, remember F equal to Ni equals to hash L. So when you increase, okay, when you increase the current, okay, you increase the hash, but at a certain point you cannot increase the B. Okay, B will keep constant. Okay, it will become saturated. So basically at this point you can use this, okay, the original one, but this, at the saturation point, the mu decrease. Okay, the mu decrease. So make sure if you given a mu naught mu r and they don't mention about saturation, you can use this relationship, but they give data B, okay, sorry, hash and B. Okay, you have a certain data. Okay, and you have something. Okay, make sure you plot it. Okay, if they give a point like this, you have to plot it because it is not linear anymore. So this is the actual or practical data of B hash curve. This is ideal. Okay, so if you already understand this, okay, so if you can see here, I is a DC, means that the current is just a constant. How about AC? So what happens if you apply AC? So let me draw again this one. So it is something like this. Okay, you have a graph something like this, and remember F is equals to Ni equal to hash L. So if you have a changing, okay, oscillated I means that your hash is oscillated. Also this one is constant, this one is constant, so I and hash will be oscillated. So at the beginning it will start, so let me B hash. Okay, So at the beginning, so make sure you understand how to draw this. So let me add a negative side because you are involving the AC. Okay. So let me, okay. So assume this is I. Sorry. I and hash. So at the beginning it will start. Let me draw a bit better. This one. Okay, this one in time domain. Okay. So you have I, which is correlate with, okay, correlate with hash. Okay. So sorry, correlate, not correlate, but directly proportional, something like that. Okay. So at the beginning, your current increase and your hash increase. So it will become something like this, a straight, and then go to saturate. And then your hash will decrease. Okay. So when your hash decrease, and remember when the hash is directly proportional to I, but B has delay. Okay, remember B has delay. So when it has delay, it takes time to demagnetize. Okay, so when it demagnetize, it's try to stay, and then it try to reduce. Okay, it will go something like this. Okay, it takes time to reduce. And then at this point, okay, because you see here hash already 0, this is hash already 0, and then it goes to the negative side. Of course it will try to decrease it. Okay, until hash is the maximum. Okay, so and then hash is reduced back, is increased back, okay, from negative side to 0. Okay, it will continue first. So let me redraw this. Okay, still not finished yet. Okay, so basically when hash is increasing, okay, it will go something like this. Okay, so until here at the maximum it will go something like this, because this one is still not maximum. Okay, this one is the maximum, and then it will go back to the positive side. Okay, go back to 0 side. Okay, negative side, maximum negative to 0. So same effect, it has delay, okay, because it needs to demagnetize. Okay, and it goes to 0. Okay, the hash equals to 0. So it will continue back to the maximum side. Okay, and it will go something like this. Okay, so basically it will shape like a leaf. Okay, so try to know how to draw this. Okay, this is, let me draw. This is the first point starting, the second point, the third, the fourth, okay, the fifth, okay, the sixth, seventh, and go back to 8, and it will repeat 8, 9, 10, 11, okay, something like that. Okay, it will oscillate here. So this is the relationship between B and hash for if the I is AC. Okay, so basically if you integrate the hash B, okay, you integrate it, okay, the area under here, okay, let me, okay, so basically what is this represent is the area here is the magnetization loss. Okay, the magnetization loss will become like this inside the area of the leaf. Okay, so this is called hysteresis. Okay, so this is called a hysteresis. Okay, and the larger the area under the BH curve here, the larger the loss. Okay, so loss, okay, magnetization loss, is the area under curve. Okay, so basically this. Okay, so if you want to find a very good material for your magnetic circuit, it is better if you choose the one with the small, okay, small area of curve. Okay, so this is hysteresis. Okay, this thing is called hysteresis. Okay, the area of hysteresis loop is volumetric energy converted into heat per cycle. So basically this area will energy produced inside here will become heat. Okay, so hysteresis loop. So this one I already mentioned here, uniform distribution, hysteresis loop. Okay, and now we move on to Faraday Law. Okay, so you have E is the electromotive force, if not mistaken. Okay, so d flux over dt, the change of flux. Okay, recall back, and equals to d flux over dt. So flux linkage. Okay, let me change this. So okay, remember this one is called hysteresis loss, so, or magnetization loss or hysteresis loss. Okay, so it's better for you to call it hysteresis loss. Okay, because this is hysteresis. Okay, hysteresis loop. So recall back E. Okay, magnetic. Okay, this one is just a voltage. Okay, basically it is a voltage. So d flux linkage over dt. So this is flux linkage. So flux linkage is basically an flux. Okay, number of flux multiply. Okay, sorry. Okay, I have technical difficulty. So let me repair this first. Okay, flux. Okay, so basically E is just the and number of flux, the flux over the this is number of flux linkage. Okay, so oh sorry, this is not number of flux linkage. This one is number of turn. Okay, so d flux over dt. Okay, so remember flux is B and area. Okay, remember flux is actually B area, so NA dB over dt. So B is equals to integrate from negative infinity to time, okay, and A dt. So I think this one no need to focus too much, but of course you have to focus the hysteresis loss. Okay, this is just a Faraday law. Try to memorize it, try to understand it, but usually we don't apply this. Okay, so this is just the way we calculate the area where the A is the cross sectional area. Okay, so we want to find the BH curve, okay, when the current is reduced. Okay, okay, we continue with this part. Okay, so basically why we want to do this is basically we want to derive the area under the curve. Okay, so this one usually come out in the theory part. Okay, make sure you try to understand how to derive this. So power is actually E and I. So I is the current, E is the electromotive force. So equals to I d flux over dt. Okay, so something like this. Okay, so I and A b dB over dt. You already derived it before, and okay, so I equals to H L. Okay, Ni is equals to HL. So P dt is the energy, okay, and equals to this one, okay. So V core multiplied by H dP. So if you integrate this, the energy, okay, it will become something like this, the area under curve. Okay, so basically this is the reason why we assume that the energy loss is basically the area under the curve. So you can see here W is equals to voltage of the core integrate with the B1 to B2 H dB. So basically the area under the curve. Okay. So this one is usually in the theoretical. So make sure you try to memorize how to derive this. Okay, I will show you. I will inform you if this one is included in the test or exam or not. Okay. So again, this is for calculating it. Okay, the area under the curve. Okay. So basically, this is the loss. Okay, this one. Okay, and the power loss. Okay, you can see here. During one cycle is basically like this one. Okay, so basically V power loss for the magnetizing core is just a voltage at the core multiplied by the area of the BH curve, okay, the area here, and multiplied by the frequency of the source. Okay, so this is how you calculate the power loss, hysteresis power loss. Okay, this one is another equation. This is one is the empirical equation. So power equals to, okay, K is the constant. Okay, constant, this one will be given depending on material. Okay, and pH is hysteresis power loss with per unit. Kb is the maximum flux density. So hysteresis loss is basically proportional to the F and AB. So this one is also important because this one is basically related to this equation. Okay, so you can see here the larger the area, okay, make sure you know the larger the area, the larger the hysteresis loss. Okay, the larger the area of VH curve, the larger the hysteresis loss, the higher the frequency, the higher the hysteresis loss. Okay, sorry about this. This note is quite unorganized at the end. Okay, so we move on to the eddy current loss. This one will be in the next video. So make sure you check in your attendance here. Okay, so pause the video and slide in your attendance. If you are in section 15, you go to the left, and the section 16 you go to right. Okay, that's it. Continue with the next video. Assalamualaikum and hello. So we continue. Let me check first. Okay, so we continue our magnetic circuit. Okay, magnetism. Okay, chapter 2a with the next losses, which is eddy current losses. So what is eddy current losses? So recall back what is the E. Okay, when okay, before I forget, so if you have a flux here, okay, I forget to explain about this. So if you have flux here, okay, so basically it will generate some kind of the voltage source. Okay, when you have flux, you will generate a voltage source inside the core. Okay, you will generate a voltage source inside the core. Okay, so what is the relationship? Is basically E equals to the flux linkage divided by dt. Okay, so remember flux linkage is N the flux over dt, because flux linkage is lambda equals to N flux. Okay, and of course flux is basically, okay, flux is equals to BA. Okay, remember B is equals to flux over area, so basically it will become something like this. Okay, so base equals to E and A dB over dt. So remember, for this case, you need to make sure that the flux is changed. Okay, if you use a DC, this will not apply. Okay, if DC, it will not apply because there is no flux linkage. There is no flux changes in the circuit. Okay, if DC, the flux is only one way, but for AC, it can go here and go here. Okay, move back and forth. Okay, so this is the voltage generated inside the core. So when voltage generated inside the core, okay, so wait, let me silence my phone first. Okay, sorry about that. We continue. So when you have a voltage, okay, E, okay, voltage, electromotive force generated inside the core. Okay, so of course the core is usually something like a circuit with resistance. So it will produce a eddy current. So you can see here. So you can look back your right hand rule, right hand grip. Okay, remember this is your thumb. So this is basically the B. Okay, and then your curved hand, something like this. Okay, your right hand grip rule. Okay, something like this. So it will produce the current. So you have the core here. You have the B. Okay, it produces B. Okay, at the same time it will produce I. Okay, inside the core. So this current, okay, this unintentional current produced inside the core is called the eddy current loss. Okay, it will go something like this. Okay, it will be closed path. Okay, depending on the resistance inside the core. Okay, so the core resistance. So this will become a loss. Okay, in form of heat. So this is another loss inside the circuit, eddy current loss. Okay, so you already know that eddy current loss occur when the unintended electrical flowing inside the core. So how to disrupt this current? So basically, how to reduce the eddy current is you use a high resistance core. So remember here, P is equals to E squared divided by R. Okay. So this is just recall the Ohm's law. Okay. P equals to V squared over R. Okay, something like that. So to reduce it, you can use a high resistive core material. Okay, like silicon, steel, and ferrite core. This one is one of the method. Or if you don't have the high resistive core material, you can use lamination. Okay, remember this is the core. You can see here, this is the current. So basically just put a insulator. Okay, so you put insulator here, you put insulator, you put insulator. So this one is called lamination. Okay, instead of one big core, you use a multiple core that is laminated together with an insulator between them. So this one lamination decrease the area of the closed path. Okay, so when you reduce the area, okay, of the closed path, you reduce the power loss. Okay, this one is the laminated thickness for the machine transformer and line frequency, around 0.5 to 5 millimeter. Okay, and for high frequency device, it is something like this. Okay, much more lower lamination thickness. Okay, so this is another losses that occur in the magnetic core. Okay, how to calculate eddy current loss? Okay, let me move this first. Okay, actually you can use software like ANSYS, Maxwell, or FEMLab. Okay, to use to find the eddy current loss. Or you can use this formula P loss. Okay, P eddy current loss equals to K is the constant, B squared is the maximum flux density, and F squared is the frequency. Okay, be careful, you have two types of losses. Okay, the first one is this one. This one is the hysteresis losses, almost the same. Okay, but K is the different K. B, if the is the maximum F, you have to square it. So F squared, B squared. Okay, don't forget B also squared, and K is also constant. Okay, this one is a different constant. So make sure you memorize the equation for eddy current losses. Okay, next we move on to the core losses. Okay, so maybe I will split the video. Okay, you already learned about the hysteresis loss and eddy current loss. So the core loss is basically the sum of hysteresis loss and the core losses. Okay, so this is just a conclusion. Okay, so basically the core losses, okay, the core losses is just equals to hysteresis loss and eddy current losses. Okay, in this one, okay, this one already explained. If you want to have a lower losses, you have to choose a smaller hysteresis loop. Okay, better have thin hysteresis loop. Okay, this one is lower losses, this one has higher losses. Okay, so next we continue with the electromagnetic induction. Okay, I will show this in the next video. Okay, that's it. Continue with the next video.